Good morning, everyone. Thank you for being here. I'm Kamran Aghaee, postdoc at Cornell University, and this project I'm going to explain was part of my PhD at Missouri S&T under Dr. Kamal Kayad's supervision. It's about optimizing crack-resistant cement paste for 3D printing using internal curing and shrinkage mitigating materials. You see here the outline. I'm going to start with the investigation method. We'll talk about the factorial design. We'll elaborate on research significance, discuss the experimental method, results, and go through the optimization process. And finally, we'll wrap up with some conclusions. The project can be divided in three parts: design of experiment, fresh and hardened properties of concrete, and microstructural analysis of the selected mixtures. Empirical and rheological properties was done by mini-slump test, marsh cone, and rheometry using concentric cylinder rheometer was done. Compressive strength and autogenous shrinkage I studied, and TGA, XRD, and MIP were among the microstructural analysis tests I've done. So let's talk about the factorial design. Factorial design is a structured, statistics-based, active regression process to determine the effect of multiple variables on one or multiple responses. It aims at optimizing the target response with the lower amount of trials, and so that it reduces the number of experiments, the time and cost of testing. It's applicable to large number of trials, but it's best to have the limited to 3 variables, and works well when the individual effect of variables and both interaction variables are significant on the target response, and reduces the potential bias by randomizing the experimental runs. So this is my mixture matrix based on the factorial design and fundamental I discussed. I had 3 variables at 3 levels. The variables were shrinkage mitigating materials, and so in common experimental work I would have 27, but I used factorial design, fractional factorial design to reduce the number of experiments. Central points were introduced by 0 coded values derived from the variables to determine the experimental errors. Validation points were used with the intermediate coded values to validate the statistical model's accuracy. You see the relation between coded and absolute values on right, and water to cementitious material ratio was 0.4 in this study. So why study 3D printing? As you know, for 3D printing and automation, we need to consider some criteria. One of the most important things is printability, which refers to effective extrusion, pumping, and deposition of the material. We need to assess dynamic yield stress and plastic viscosity. To address that, we need to also consider buildability, which is sustaining weight, retaining shape without formwork, and providing proper bonding in the layers. So static yield stress and thixotropy are the main factors to consider in this area. We need to consider mechanical, including bonding among the layers and mechanical properties, shrinkage, and as we know, high content of cement, and the previous presentation also mentioned, makes concrete vulnerable to shrinkage, cracking, and lack of curing, formwork, and exposure to ambient temperature are also other factors that make us consider this shrinkage problem, plastic and drying shrinkage. High porosity at the interlayer also due to the lack of consolidation, and curing is a point of concern. I use these 3 materials you see on this slide: expansive agent, shrinkage reducing admixtures, and super absorbent polymer. Briefly, initial expansion by expansive agent reduces the later age shrinkage reducing admixtures on non-ionic surfactant reduces the surface tension of pore solution. Super absorbent polymer are internal curing materials, polymetric. They absorb a lot of water quickly and release to the matrix gradually to extend the hydration and compensate for the self-desiccation. You see the material properties. I use type G, which hydration products is potendite, and for the expansion. SAP with D50 of 52, water absorption and desorption of 30 gram per gram and 95% in 2 weeks was used, as you see on the right graph. Fresh properties was studied empirically and with rheolometer. You see the hysteresis loop on at the bottom. The Bingham linear Bingham model was fitted to the descending curve to calculate the dynamic yield stress and plastic viscosity. Thixotropy was measured between the ascending and descending curve, area between the ascending and descending curve, and at a shear rate of 20 and 80 per second. And Marshcombe flow time is shown on this slide. Initially, the mixture with with high percentage of SAP didn't allow us to complete the test because high water absorption of the SAP particles and expansion reduced the flowability. The same mixtures after 90 minutes, and the ternary mixture, including all the variables, also was so thick and we couldn't complete the test. Mini slump and apparent viscosity at initial shear rate, and Marsh cone flow time and apparent viscosity at 100 shear rate were correlated. You see good correlation, and the system, including all the materials, ternary system had had a high apparent viscosity in both low and high shear rate. Made us to conclude that this is not a good candidate for 3D printing. As mentioned, for rheological properties of 3D printing concrete, we need to consider pumpability and buildability. Initially, we need high pumpability, which is I evaluated based on the 20-minute plastic viscosity to be low, and 90-minute static yield stress for buildability to be the highest. The best combination for pumpability was combination of SRA and SAP, and the best for buildability EA SAP. Compressive strength is shown on this slide. As you see on the right, column chart shows that including the individual use of shrinkage mitigating materials reduce the mechanical properties, and when the internal curing using SAP and other shrinkage mitigating materials applied, significantly drop in strength up to 50% was observed. And the best combination was, based on the contour graph you see at the bottom, was the combination of EA-SRA, and the worst was SRA-SAP. And as you compare, you can see at the top, dry SAP and wet SAP, you can see the high expansion of the particles due to the water absorption, and after release of water, they leave voids in the concrete and reduce the mechanical properties. Autogenous shrinkage is shown on this slide. The excessive expansion by EASAP system and ternary system due to the additional supply of water by superabsorbent polymer and extension and continuous expansion of the expansive agent led to visible cracking. As you see, I got excessive expansion for the those. And other than that, other mixtures were good. The best combination was EASRA and SRA-SAP. The worst was EA-SAP. Microstructural analysis are shown, and as you see for the TGA, I got highest peak for portlandite for the half SAP 10 EA mixture, which again is a representative of high amount of potlandite due to the water supply and expansive agent hydration. And on the XRD table on the right, you see when comparing the reference mixture with SAP mixtures and their combinations, we get higher hydration products, shrinkage and potlandite compared to the reference mixtures, and in contrast, lower unhydrated C3S and C2S compared to the reference. But this wasn't enough to conclude about the compressive or mechanical properties. Comparing MIP, you see the lower median pore size for reference and total porosity for the reference compared to that other mixtures, which can describe the significant mechanical properties reduction. Optimization based on the criteria I mentioned, which were reducing the initial plastic viscosity, maximizing static yield stress, and match target in the software was used, which is an indicative of the intermediate level of that variable, not excessive high, not low. And 28 days mechanical properties, compressive strength was said to be the highest. And based on that, you see the derived statistical models with pretty good R squares. And I candidated 3 combinations of these systems, including EA and low amount of SAP, EA, low content of SRA, and individual EA. In conclusion, shrinkage mitigating materials increases the static dynamic yield stress, plastic viscosity, and thixotropy. EA-SAP combination almost tripled the 90-minute static yield stress. Individual shrinkage mitigating materials significantly reduced and combined eliminated shrinkage, and also they reduced significantly, especially in combined situation, the mechanical properties, and SAP mixture due to the additional water and absorption of water and swelling and leaving void after desorption led to inferior mechanical properties. 10 EA mixture and 10 EA include with low content of SAP and SRA were the best flowable thixotropic with high pumpability, buildability, and high strength almost without autogenous shrinkage applicable to 3D printing. I would like to thank to Dr. Kamal Kayat for support on this project, and Dr. Ricardo Esposito, my colleague who collaborated on this. These are references, and thank you for your attention.